Welcome to this Maths Methods 3 and 4 revision video on Chapter 6, or at least Part 2 of Chapter 6, Circular Functions. And as usual, please note the questions and examples used in this video are taken from the Cambridge Essential Mathematical Methods 3 and 4 CAS textbook. No intention has been made to infringe copyright, and my apologies if it has. However, this video is simply a resource for my current students to assist in their preparations for the VCE examinations. Thanks for your understanding. So what did we discuss in our last video? We were looking at our unit circle, and if you remember, we had all stations to Canberra, and we had a number of identities that we had developed that would allow us to find various values of sine, cosine and tangent. Now, while the unit circle is incredibly powerful, that wasn't the way I was taught at school. Back in the day with United Kingdom, when we had nothing but chalk and blackboards and dinosaurs roamed freely outside. Yeah, really must do something about those dinosaurs. But this didn't make a huge amount of sense to me personally. It does now, thankfully, maths teacher. But we had to use something quite interesting and perhaps quite simple. And they were these three graphs. Yich, I might hear you say, but actually not so yich. Now I've taken these out of the textbook so that you've got a reference, but this graph here effectively is the sine curve. Alright, so it's graph plotting values of sine theta, alright, against y. So these values up here are y values and across are sine theta. Now these values are given in terms of radians, which is fine, that's not a problem. What can we see? Well, first thing we can see is our graph is cyclic. It actually is a cycle, and it's also repetitive. Now the repetitive nature of this means that this has what we call a period, right? And a period is basically the distance between the start and the next start. If we look at actually where this graph starts, and we suggest it starts at 0, then it reaches back at 0 again before it continues up. And so we say that the graph of the sine curve has a period of 2 pi. Seems sensible. And if we look at the height this graph goes, well, if we look at, again, starting at 0, and the highest this graph goes, what we see is the highest it goes is 1, and the lowest it goes is -1. Now, the difference between sort of where it starts and where it finishes in the height sense, you know, from the middle to the top, or I suppose from middle to the bottom, is called the amplitude, all right? And so the amplitude of a standard sine curve is given by the number 1. All right, so it's given by the number 1 because the height of that is 1. And the range, well, the range of a normal sine curve is given between -1 and 1. Remember, range is our vertical height, so our standard range is between -1 and 1 inclusive. So that's our sine curve. What about our cosine curve? Well, the great thing about the cosine curve is pretty much it's the sine curve that's just been shifted pi on 2 that way, right? It's exactly the same, right? So it has the same period. It has the period of 2 pi, right? Or for those of you who are degrees purists, 360 degrees. What about our amplitude? Well, if it's the same as the sine, then the amplitude is also 1 unit. And the range? Yup, absolutely the same. The range goes between -1 and 1. The only major differences between the sine and the cosine curve, I suppose you could say, is the start point. Here, when it is 0, what we notice is it starts at the value of 1, right? And it finishes here again at 2 pi, but at the value of 1. Our last graph to be aware of is the tan curve, and I have to say I love the tan curve. Now this situation, it has a period of just pi, right? It actually repeats every 180 degrees, and what you notice is there's the crossing point, and there's our similar crossing point, or it starts again there, and that distance is literally pi. Don't worry about the numbers underneath at the moment, the -3, -2, -1. We'll come back to those shortly. So the period is pi. It doesn't have an amplitude, right? It doesn't have an amplitude, right? Because what we can see is this thing goes on to infinity, all right? Our range is from -infinity to infinity, and obviously we can't include those. Having got the general ideas here, what I also want you to notice is about where these graphs are positive and negative. If we, roughly speaking, draw a dotted line through pi on 2, through pi, through 3 pi on 2 and through 2 pi on here, what do I notice? Well, it's positive in our first section, right? It's positive in only our first section. What about if we do the same here and here and 3 on 2 and 2 pi? Where is it positive? It's positive here in our first section and it's positive here. Right? Where else is sine positive? Yep, it's also positive here in our first and second section. And what about tan? Well, again, we've already actually got these dotted lines pretty much. You may be wondering what these dotted lines are here. They're asymptotes. They're a point where the tan graph will never ever go through, all right? So also a pretty important part of the graph. But if we look at where our tan is positive, it's positive in the first section, right? Now it doesn't line up, but this is our first section and our third section. Well, if we were to go back to our whiteboard and look at this again, what did we notice? Well, all of them were positive in the first quadrant, sine in that one, tan in that one, and cosine in that one. So we've just realistically proven the same piece of information but with the graphs. Sine is positive in the first two quadrants, so they're all positive in the first quadrant, sine, tan, and cosine. Now, whether you use these graphs or not is a completely different matter, but this part of the chapter is all about dilating, translating, and reflecting graphs, so let's move on with some of the excitement. So if I have the idea that I want to sketch the graph of y equals 5 sine 3 theta, what does that actually mean? Well, we can look at the idea that it's got something to do with the graph of y equals sine theta, and we know roughly speaking what the graph of y equals sine theta look like. It's this curve shape where we have 0, pi, and we have 2 pi. That's a standard, remember? It has a maximum height of 1 and a maximum height below, or a middle height of -1. So our amplitude is 1. So what do we reckon this is? Well, we've seen this number before. Any number in front seems to be a vertical shift or away, or a dilation away from the x-axis, and that's exactly what this is as well. This 5 tells us that this graph is going to be dilated by 5 units away from the x-axis. What about this value here? Well, again, it's beside theta. Now, if we imagine that was an x, we've met that before. If this was actually y is equal to the sine 3 of x, we're pretty much sure that anything that's stuck to the x has something to do with an x dilation, but in the opposite way that we thought. Now, that doesn't actually stretch this graph out by 3. What it actually does is it squidges it in by 3. So that is actually a 1/3 dilation from the y-axis, right? So it's a 1/3 dilation from the y-axis. Well, how does that now mean we can draw our graph? Well, first things is it actually going to shift? Does the graph move left or right? No, it doesn't. It's actually just going to squidge. So we now know that our maximum height is going to be 5, and the minimum height is going to be -5 because it's stretched up. It's stretched this way 5 units, and it's obviously stretched that way 5 units as well, away from the x-axis. And what about these crossing points? Well, they're just going to be 1/3 of the way, right? Why? Because we're taking all of our x-coordinates and we're dividing them by 3. That's what this 3 here means, and that's what that 3 there means. So it's going to start at 0 again, but now we're going to cross through at pi on 3 and 2 pi on 3. Now, you're not going to see a major difference in sense of accuracy, but generally speaking, there's my graph. What's important to show for an examination? You need to show your maximums and minimums, and you need to show your crossing points at the same time, you know, with a little bit of an idea of theta or x and y, whatever it's going to ask along the bottom. But yeah, pretty much, dilations work in exactly the same way as they have done before. Now, if we want to try and find out what the period is of this graph, all right, the period, and if you remember that's the difference between when it starts and finishes, well, a shortcut is using the formula that period is equal to 2 pi divided by, and I'm going to say, modulus of n. Well, what on earth is a modulus of n? Well, these equations here can be written in terms of y is equal to a sine, and then in brackets, nx. So what it's saying is this value here in front of the x is what goes below here. Well, that would have made n in our case 3, So if we just look at this, it would have suggested that the period of the graph above would have been 2 pi upon 3, and is that where our graph finished? It actually was. What about our amplitude? Well, again, looking at the general form here of the equation, we can find that the amplitude is basically equal to the modulus of A. Whatever value is in front of this, right, the amplitude becomes. So, did it become 5? Yep, because it stretched up 5. So that's dilations, swiftly covered. I suppose it would then make sense now to deal with reflections. So, what would happen if we have a function of x is equal to sine x, and I want to reflect it in the x-axis? If I want to reflect it in the x-axis, it's all the y values that are changing. So I would imagine then that if we have our standard sine curve looking like this, what is our reflection going to look like? Yep, like that. Okay, they're not supposed to be exactly the same lining under. It's not that easy on here. But this would be 0, again pi, and 2 pi. It would still have an amplitude of 1, but it would just flip. So what would our equation look like? Well, our equation would look like, if this was y equals sine of x, this would be y is equal to minus the sine of x. And what about if we were being asked to find the 5 sine of minus 3 theta? Well, we now know that 5 is our amplitude, 3 is going to be a dilation, a factor of third. But what about this minus sign in here? Well, if the minus sign was outside and it was a reflection in the x-axis, then a minus sign inside must be a reflection in the y-axis. So we've got our standard graph here. What would our reflection in the y-axis look like? Well, it would look sort of like this, right? And so what would my maximum be? Well, my maximum would be 5. My minimum would be minus 5. What would my crossing points be? Well, that would be pi on 3. And that would be 2 pi on 3. And pretty much, I think that's my graph. Using this information and all the information we've had before, we can now start to dilate and now reflect our sine curves. And this works in exactly the same way as cosine curves. Translations. How do translations work? Well, let's think about it. What if I had y is equal to sine of x plus 1? Hopefully, you've got enough knowledge now to realise that plus 1 is going to be a vertical shift. If my standard sine curve looks like this and has 1 and minus 1 and goes between pi and 2 pi, what is this graph going to look like? Well, firstly, and I tend to draw dotted lines, if this whole thing's moved up by 1, I'm going to have it go up by 1. All right, so there's my 1. It now means that the highest point of my graph is going to be 2, and the lowest part of my graph is going to be 0. Why? Because this thing here still has an amplitude of 1. It still has a height of 1. What about my crossing points? Do they change? Nope, because it's a standard sine curve. So there's pi, there's 2 pi, and what we end up doing is drawing our graph to look roughly like that. All right, now it's supposed to be symmetrical and it's supposed to be even, but I'm just trying to give you the general ideas at this moment in time of what the various things do. All right, what does our period become? Well, our period is still 2 pi. And what is our amplitude? Hopefully you'll realize it's still 1. And what about our range? Well, our range is going to go between 0 and 2 inclusive. Why? Because the lowest value is here at 0 and the highest value is here at 2. Ooh, it's exciting. But what about the value y equals sine of x minus pi on 3? Well, it's inside my bracket, so what does it mean? Well, this isn't going to be a vertical translation, this is going to be a horizontal translation, and it's going to translate in a completely different way than we thought before, i.e. the minus sign we tend to think may move that way, but it doesn't, it moves that way. So we've got our standard again, looking at the top yellow graph. How will this look? Well, I don't need to move it up or down or anywhere. All I need to realise is, well, it's going to move pi on 3 to the right, so it's actually going to start, when we use that start term advisedly, at pi on 3. Then where is it going to go? Well, it's going to go through here? Well, it normally crosses at pi, and I want to do pi plus this pi on 3 shift. What does that give me? That gives me 4 pi on 3. Yep. And then 2 pi plus pi on 3, because again it shifted. It was 2 pi, but it's going to move that way by pi on 3. So what does that give me? That gives me 7 pi on 3. Now we could have probably worked that out quite quickly, because if we know that the difference between here and here is 3 units, because I've gone from 1 to 4 pi's, then it must be 3 units, and that will continue repeating throughout my graph, right? And this way as well. A lot of people think the sine curves only go one way. They don't. So can I now draw this? Yep, is my amplitude going to change? Nope, because the number in front of there is still 1. So there's 1, and there's -1. Okay, we're going to have the graph go up, and down, and up, and theoretically speaking, and down, and we should actually continue this, and down, and up, right? But I'm just trying to give the idea that when you are shifting this, you are looking at making sure that your crossing points and your amplitudes are all the same. So this value inside here is a horizontal translation, right, in the direction of the x-axis, as the book seems so fond to suggest. And obviously I think we can join these all together and come up with something along the lines of y is equal to 3 sine 2 t minus pi on 4. Oof, what does all that mean? Well, let's start with the easy stuff first. This 3 here is going to be what? Yep, it's going to be a dilation away from the x-axis. So it's a factor 3 dilation away from the x-axis. What do you reckon this 2 means? Yep, that's going to be a dilation factor 1/2 from the y-axis. And the value inside, yep, it's going to be a translation of pi by 4 units in the x-axis direction, right? So can I now work out anything about my period? Yep, well we can probably just say, well, our period, if you remember, is 2 pi divided by the modulus of n, and in this situation n is 2, so that's going to have a period of pi units. And what else do we know? We know that our amplitude is going to go to be 3. Why? Because this value in front of here is our amplitude. And so I can pretty much say that my range of this graph is going to fall between -3 and 3. Why? Because it's not being moved vertically. It is not being moved vertically. So let's have a look at trying to draw a quick sketch of this graph. Okay, so we know the maximum is going to be 3 and the minimum is going to be -3, so that takes care of my range and my amplitude. My period is going to be pi, but I've got to take account of this pi on 4 shifts. So it's going to, quote unquote, start at pi on 4, and the next one is going to be at 5 pi on 4. Why? Because it normally crosses at pi, and I've shifted it pi on 4. So if I do pi plus pi on 4, I get 5 pi on 4. I can now work out the rest of mine quite quickly, because if I've added 4 onto there, I add 4 on to keep getting to my next crossing points. So I'll get 9 pi on 4, and what else? 13 pi on 4, etc, 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 and -3 pi on 4 on this side of my curve. Right, remember, I can take 4 off as well, so the add 4, add 4, add 4, and now I think pretty much I've got everything I need to be able to do to sketch this. And again, I'm going to apologise because this is going to probably look pretty shocking, but it's going to go up and down through there, and up and down and up and down and down and up, and yep, that is probably a pretty shocking sine curve. But again, it's the information. You can draw that probably much better than I can. But again, what have I got on? I've got my maximums and minimums, got my crossing points on, and I suppose I should work out where that actually crosses the y-axis. How do we do that? Well, what do we know? We know t is 0, and we can use our CAS calculator. So, not too much really now to be able to use the ideas of translations from all the work we've done previously. If a graph crosses the x-axis or the y-axis, then ideally we should be showing, and I imagine in our VCE examination they're going to expect us to show what our intercepts are. Well, let's look at a quick example of y equals √2 sine x plus 1. Right, well, what do I know about this? Well, let's look at the idea of period, amplitude and range. And I'm just going to PAR, which reminds me of a previous deputy head teacher I had to work for. Shut up. So, what does P stand for? P stands for period. What's the period of this graph? Well, there's no number by the x, so the period of this is going to stay as 2 pi. The amplitude, well, the amplitude is changed, so it's going to be root 2. And what is my range going to be? Well, okay, so this plus 1 means it's going to move my graph up 1 unit, so I'm going to have the value of 1 plus root 2 is going to give me my maximum, and 1 minus root 2 is going to give me my minimum. So my range is going to go from 1 minus root 2 to 1 plus root 2 inclusive. That seems pretty easy. We quite like that idea. Maybe we'll use this and adopt it. So there we go. We've got a period, we've got our amplitude and a range. It doesn't seem to be shifted. There is no horizontal translation. Why? Because there's nothing in the x. And there's no dilation away from the y-axis because there's nothing in front of the x. So that's pretty cool. So we've got information, but right, well, if we now look at trying to plot this graph in a roundabout sort of slanty way, what do I know? Well, I now know that I'm going to draw a dotted line because this thing has moved up 1 unit. And what do we know? We know that it's going to have 1 plus root 2 as and 1 minus root 2 as a minimum. Now that now suggests to me that I'm actually going to end up with some crossing points in my x-axis. Why? Well, normally we'd have pi and 2 pi because this thing hasn't been shifted. And what do we find? Well, this thing is going to go up and down and up, right? Probably one of the nicest sine curves I've drawn today. We are theorizing at the end of the day that this is where it's going to be, but I'm pretty sure that these crossing points are going to be important to us. Well, how do we find crossing points on the x-axis? Well, we know that on the x-axis, y is equal to 0. So therefore, we just equate. We put root 2 sine x plus 1 is equal to 0. So root 2 sine x equals minus 1, shifting this over. And sine of x is equal to the negative of 1 over root 2. Well, using my CAS calculator, that gives me x is equal to minus pi on 4, and the world goes crazy, but actually, no, it doesn't. There are two things I've deliberately not talked about, and that is, where does it actually want us to know these solutions? Remember, I've only drawn one part of the curve here. It goes to infinity and beyond that way, and infinity and beyond that way. There has to be a way for the examination to tell us between limits. Where do we start this graph and where do we end? Or where is our consideration going to be? Well, actually, for this particular graph, what it wants to know is x is included in 0 and 2 pi. In other words, it just wants us to do between here and here. Well, that would suggest then that actually my first value of negative pi on 4 is completely useless to me, right? That's no good to me at all. So how do I get from negative pi on 4 to some values that actually make use of this to me? Well, let's do a very quick all stations to Canberra. Where is that going to be? That's going to be down here in negative pi on 4. Right? That's going to be pi on 4 under there. So we've got all stations to Canberra. Well, the only other place it's going to be negative is here. So that's also going to be pi on 4. So how do I find values between 0 and 2 pi where they're negative? Well, I just look at things around this way, right? So that's going to be pi. So my value of x, my first value of x is going to be equal to pi plus pi on 4. And my next value is going to be this one, and that's also 2 pi. So 2 pi minus pi on 4. That will put us in the right order, which gives us 5 pi on 4 and 7 pi on 4. And so what do I now know? I now know I've got my crossing points. This crossing point here is 5 pi on 4, and I know this crossing point here is 7 pi on 4. So I'm now using my graph and this all stations to Canberra unit circle to help me find solutions. We don't need to find the solution here. We don't need to know the crossing point there. Why? I think possibly we already know that. All right. Another example where we maybe have something in here. And let's do that now. Let's have y is equal to 2 cos 2x minus 1. Well, let's think about this. So what is my period going to be? Oh, I've got a value in front of the x. So here it's going to be 2 pi divided by 2, which is pi. So my period is pi. What is my amplitude going to be? Well, there's a value here. So my amplitude is going to be 2. Oh, I've got a vertical shift. So my range is going to be, my range is going to go from -1 plus 2 and -1 minus 2. So -1 plus 2 is 1 and -3. So my range is going to go from -3 to 1. So let's see, quick. Oh, I'm getting much better at these axes. Ooh, the excitement. And I'm talking to myself again, which I've been doing for the whole video. Anyway, so what do we do? I'm going to draw a dotted line through -1. And there's -1. And I know now my period is pi. So that means that's going to be pi on 2. And there's going to be pi. Oh, have I missed anything off? Yep, we need to know our limits. That's going to go between 0 and 2 pi again. So I'm going to need another one and another one, all right, because we're shifting this graph in. So that's going to be 3 pi on 2 and 2 pi. What do I know? I know that the maximum of this thing is going to go to 1 and the minimum is -3. So I'm in a position now to be able to draw this. Yep, I think so. So remember, this is a cosine curve and we're trying to work out where this is going to cross on our x-intercepts. Now we could draw a diagram. I think we draw a diagram. Yeah, because it's got to be a minimum here and it's going to be back to here. So it's going to look something along the lines of, oh, that is dreadful. And again, it's going to have a minimum here and back to here. Yep, that is just dreadful. But what I'm trying to illustrate is this thing actually has some crossing points. Where are our crossing points going to be? Well, it looks like we've got 1, 2, 3, 4. How can we find them algebraically? Ooh, this is the excitement. Well, we know now how to find our x-axis crossing points because we put this equation here equal to 0. So we have 2 cos 2x minus 1 equals 0. 2 cos 2x equals 1. Or the cos of 2x is equal to 1/2. So using my calculator, you know, I could go cos to the minus 1/2, or I probably already know it, and what does that give me? It gives me pi on 3, right? But that's only one value. Looking at my graph here, I find that actually I need 4 values. Why 4 values? Well, it goes back to this idea here of my dilation. A standard cosine curve between 0 and 2 pi will give me just 2 solutions. But if I've dilated this thing and I've squeezed more than one between my standard, then surely if I have a period of pi, that means I must have 2 cosine curves squared into. I must have 2 cosine curves fitted into a standard. Well, if a standard one gives me 2 and I've got 2 fitted in, I must have 4. And that explains why I've got 1, 2, 3, 4 crossing points between my period, my standard period of 2 pi. So I've got my pi on 3, how do I find the rest of them? Ooh, let's use our all stations to Canberra, all right? So here's my first one, pi on 3 there. And where's my other one going to be? Well, it's going to have to be in this one because that's my Canberra and that's my all. So that's 2 pi. So I know my first one is pi on 3. How do I get to my next one? Well, I must do 2 pi minus pi on 3, which is 5 pi on 3. So I now know my next one is 5 pi on 3. Ooh. So how do I find my next 2 values? Well, remember, at this moment in time, I know that we looked at the period being pi, but we're still dealing with the standard cosine. We did inverse cos of 1/2. So how would I find my values for a standard cosine curve? Well, if it's repeating as normal with 2 pi, how do I get to my next value? Well, I take pi on 3 and I do 2 pi plus pi on 3. And what does that give me? 7 pi on 3. And now add 2 pi onto 5 pi on 3. So I'm going to do 5 pi on 3, add 2 pi. And what do I get? I get 11 pi on 3. Now I don't need to worry about any more values because I'm expecting 4. I only need 4. But, and I know this is looking untidy now, but still work with me, we're looking at the values at the moment of just 2x's. These are the values of 2x. We're looking for these values here, which are the values of x. How do I get them? Well, obviously you divide everything by 2. So I get pi on 6, 5 pi on 6, 7 pi on 6, and 11 pi on 6. What does these values mean to me? Well, now you have found exactly where these things have crossed, right? It is going to cross at pi on 6. This value here is pi on 6. This value here, 5 pi on 6. This value here, 7 pi on 6. And this value here, 11 pi on 6. I really do suggest you running back over this again just to make sure you understand why I'm dealing with the ordinary cosine curve here and only getting back to this one here in that line. I'll do one more example. Well, let's look at the graph of y equals 2 sine 2 and in brackets x minus pi on 3 minus root 3. And the reason I've just done that 3 on the bottom is because I misread my own handwriting for the second time of doing this question. So probably when I edit this actual video is going to go from something like 7 hours down to about 30 minutes, one hopes. So let's start again. How do I find my x-intercepts? I make y equals 0. So if we make y equals 0, I get 2 sine of 2, and in brackets x minus pi on 3 minus root 3 is equal to 0. We do a bit of shifting around, so we get 2 sine 2x minus pi on 3 equals root 3, and so sine of 2x minus pi on 3 is equal to the root of 3 upon 2. And just for information why, that minus root 3 moves over and that 2 moves over as well. So I've now got something I can deal with. I am trying to get rid of my sine because we're dealing with my standard sine curve. So let's think about, right, okay, well, how do I do that? Well, I do sine to the minus 1 of root 3 upon 2. And using my calculator or just my basic knowledge, what do I know? Well, I know that that first solution is pi on 3. The question is, how many solutions am I looking for? Well, we go back to our idea of our period. What is the period of this particular function? It's going to have a factor 2 dilation from the y-axis, which if you realize or remember, you do 2 pi divided by 2, so it's pi. So we are going to have this graph squidged. Or, more importantly, if we are going between the domain of 0 and 2 pi, and I've got pi as one of them, I'm going to fit 2 lots into my standard. Right, I'm going to fit 2 lots into there. Well, a standard graph has 2, so we are looking for 4 solutions. There's my first one as pi on 3. So we can now write this down as 2x minus pi on 3 equals, and my first solution gives me pi on 3. How do I find my next solution? Well, we draw out all stations to Crewe, or all stations to Canberra, because I'm in Australia. And what do we find? Well, there's my first one of pi on 3. And there's my next one on pi on 3 because that's where sine is positive. And so we know that pi on 3 is my first one. If that's pi and I'm not quite there, I've got to work out what pi minus pi on 3 is. And yes, I get 2 pi on 3. How do I get to my next 2? Because I've got 2 more I've got to find. Well, because we're still dealing with the standard sine, to get between each of these values and the next ones, I would just add on 2 pi. So I'm now looking for 2 pi plus pi on 3, which is going to give me 7 pi on 3. And my next one, well, if that's got 1 pi added onto it, or rather if that's got a third of a pi added onto it, that's also going to have a third of a pi added onto it, gives me 8 pi on 3. So there are my 4 solutions, but remember that's for my standard sine curve. We now need to rearrange it, or we now need to transform it using the algebra that I now know. Well, if I'm trying to get the x on its own, which effectively I am, the first thing I've got to do is get rid of the 2. So I'm going to divide everything by 2. So that leaves me with x minus pi on 3 is equal to pi on 6, 2 pi on 6, 7 pi on 6, and 8 pi on 6. Good. And what do I now do? Well, I want to get x on its own, so what do I need to do? Yep, I've got to add on pi on 3 to each of these values, or 2 pi on 6, right? So that's just pi on 3, remember, will be 2 pi on 6. So I'm adding on 2 to all of the top numbers effectively. So I'm going to get 3 pi on 6, and I'm going to get 4 pi on 6, and I'm going to get 9 pi on 6, and I'm going to get 10 pi on 6. All right, and so what can we now do? Well, we can do a little bit of Well, no cancelling down. And what do we find as our final crossing points? We find our crossing points would be pi on 2, 2 pi on 3, 3 pi on 2, and 5 pi on 3. Now I don't have room to draw this graph, but just remember that this would now have a vertical translation of minus root 3 down here. It would move that way by pi on 3. It would be squidged by a half, and it would have an amplitude of 2, right? So you should now be able to find out your ranges and your maximums and minimums and be able to do a pretty good idea of what this graph is going to look like. Well, that's the algebra for this section pretty much finished. How are we going to use it in other examples? The textbook talks about addition of ordinates, and we've already worked out in previous sections that if you want to add ordinates, if you had, as they suggest, a graph 2 sine x and another graph of 3 cos 2x, and you wanted to find the graph where you added those together, well, that's literally what you do. You do the graph of y equals 2 sine x plus 3 cos 2x. Now in this situation you'd have to look for various crossing points and maximums and minimums. As far as I'm concerned, if you would need to, you'd use your calculator, alright? But I would use your calculator to sketch that graph, sketch them together, and just transform it onto your examination paper, if it's a CAS-enabled paper. The next section is just basic algebra, and it goes on about the idea of determining rules for graphs. Well, if they actually give you a graph and you know things like the period, you can work out your period, you can work out your amplitude, and you can work out your range, then you should be able to fit into just basic algebra the idea. So it's difficult for me to talk much about that. Just revise it from page 234 in the textbook. Tan, funky, we love tan. We've already looked at the idea of the tan curve. Is the algebra any different? Not really. I'll just do an example. So what would we have if we wanted to find, I don't know, the graphs of y equals 3 tan of 2x minus pi on 3, and we wanted to go between the values of pi on 6, this is weird, and 13 pi on 6. Well, we'd probably want to find our crossing points, or we could look at things along the lines of dilations and translations and what have you. Well, let's do that. This, we're hopefully aware now, is going to be a dilation away from the x-axis of factor 3. But what about here? I'm not used to seeing 2x. Well, we can use a bit of an algebra trick by saying y is equal to 3 tan, and I can actually take a factor of 2 out of those brackets, and it gives me x minus pi on 6. So I now know that this has a period of pi on 2. Why would it have a period of pi on 2? Well, if you remember, the standard period of a tan curve is pi, and we're dilating it by a factor of 2, so it's going to be pi on 2. And what about this, minus pi on 6? It just means the graph is going to be moved that way, pi on 6. So I think probably I have enough information here without finding any x-axis intercepts to work out what I need to do, but we'll do it anyway. So we know that to find the x-intercepts, we just put y equal to 0. So we'd have 3 tan 2 x minus pi on 6 equals 0. Well, we divide both sides by 3, it gives tan of 2 x minus pi on 6 is equal to 0. And so what is the inverse tan of 0? So tan to the minus 1 of 0. Let me see, what's the tan to the inverse minus 1 of 0? Well, it's 0. So I now know that 2x minus pi on 6, first solution is 0. Where will my next solutions be? My solutions would ordinarily be at 0 and pi and 2 pi and 3 pi. And how far do we go? Well, that's the interesting question. Remember, this has a period of pi on 2. It wants me to go between pi on 6 and 13 pi on 6. So let's just rewrite our period in terms of pi on 6 is going to be equal to 3 pi on 6. So how far is it between pi on 6 and 13 pi on 6? Well, that has a distance of 12 pi on 6, and I've got a period of 3 pi on 6, so that means that we're going to fit that into there 4 times. So if a standard tan curve has a crossing point of just one crossing point between 0 and pi, we're going to be looking for 4 crossing points, right? 0, pi, 2 pi, 3 pi, and 6. Right, let's see what we come up with these values. So let's divide by 2. It's going to give me x minus pi on 6 is equal to 0, pi on 2, 2 pi on 2, and 3 pi on 2. Do we think those are our crossing points? Well, let's work it out. So we're going to move now, add pi on 6 to everything. So you're going to get x is equal to pi on 6, 4 pi on 6, 7 pi on 6, and 10 pi on 6. All right. So are they our solutions? What would the next one be? Well, the next one would be 13 pi on 6. And actually, that would fit in. So I missed a value off. That should have been 4 pi. Right? That should be 4 pi upon 2. And I should have an additional one of 13 pi on 6. Which, if we were to use a bit of bad spacing, what do I get? I get my x-axis intercepts as pi on 6, 2 pi on 3, 7 pi on 6, 5 pi on 3, and 13 pi on 6. So there we go, right? So sometimes this guide of using the period and all the maths I did here isn't always accurate, so sometimes you need to check, or you don't want to make a mistake. Drawing towards the end of this video, we get the idea of trying to find solutions of equations such that you have sine of nx is equal to the k cos of nx, right? So a simple example of sine of 2x is equal to the cos of 2x. Now this is a huge trick, and it uses one of the simplest trig identities in the world. It uses the idea that tan of x is equal to the sine of x divided by the cosine of x. And if you have a sine and a cosine in the same equation, looking similar like this, they're just asking you to divide, because what you're going to find out is sine of 2x divided by the cosine of 2x is equal to 1. Right? Because you're going to divide both sides by cos 2x. You have tan of 2x equals 1, and you know how to do the inverse tan of 1. Tan to the minus 1 of 1 is basically pi on 4, and so you'd end up with 2x is equal to pi on 4. Where would my next one be? Well, it repeats every pi, so you'd have 5 pi on 4, etc., etc., etc. And then you would just divide that by 2 to give you pi on 8 and 5 pi on 8, and so you would go on, ad nauseum, or between wherever you needed to go. And let's just assume that this went between 0 and 2 pi. Well, then that would suggest that there were at least another 2 more I could find, because there would be 9 pi on 4, and there would be 13 pi on 4. And how do I know that? Because if I divide these by 2, I'm going to get 9 pi on 8, and I'm going to get 13 pi on 8, none of which are bigger than 2 pi, and there are my solutions. So a bit of a trick there, really. It's using this idea that tan is equal to sine divided by cos. The very last section of this chapter deals with general solutions, and I know that it's one of those things in the exam that has caused a number of people some confusion, because when it starts talking about general solutions, it's like, well, what does that actually mean? Well, there are a number of formulas that if you have the cosine of x is equal to a, what it is trying to say is that your values of x can be found by 2n pi plus or minus the inverse cos of a. All right? I'll explain what that means in a moment, but that is quite important. Cosine only has one general solution. Same with tan. They are saying if you've got tan of x is equal to a, then what you're trying to suggest is that x is equal to n pi plus the tan to the minus 1 of a. Right? Another formula that's quite important. Sine is the tricky one, right? Sine actually has 2 formulas, which is minorly irritating, but it's useful to write these down and have them in your notebook. And it suggests that if you have sine of x equals a, then firstly you get x is equal to 2n pi plus sine to the minus 1 of a. That will give you half of your solutions, right? Or, and what it means actually is and, because there's another lot, x is equal to 2n plus 1 pi minus sine to the minus 1 of a, all right? And if you've done any of these questions in the exam, you'll probably start to find that actually, yes, there are more than one solution. So just to give the idea of an example, all right? But seriously, learn these, very important. So I'll do a sine example. If you've got 2 sine x is equal to root 2, then you know that sine of x is equal to root 2 over 2, and you now know what your first solution is, right? You know that the first solution of that is going to be pi on 4. So if we go back and look at what it's asking, then Sine says that your general solutions are given by 2n pi plus sine to the minus 1 of a, and or given by 2n plus 1 pi minus sine to the minus 1 of a. Right? Well, this sine to the minus 1 of a is pretty much what we've just found here. So writing it more specifically for here, what I can now say is that my values are given by x is equal to, or my general solution is given by 2n pi plus pi on 4, or 2n plus 1 pi minus pi on 4. So those are my general solutions. Those are the formulas. How would I then actually find out my values? Well, you substitute in values of n, for example. Right? You substitute in values of n. And what would we end up with? Well, if n was 0, for example, then we'd find our first solution is pi on 4, which we know. If n is 1, we get 2 pi plus pi on 4, which would be 9 pi on 4, and so it goes on. And likewise here, if n is 0, you'd end up with pi minus pi on 4, which would be 3 pi on 4, and you'd end up with, if n is 1, 3 pi minus pi on 4, which would be 11 pi on 4. So something that actually comes over as really quite complicated isn't, and we could probably write these in a different form, because if you've got 2n pi plus pi on 4, you can take pi as a factor out. If you were to actually put this as one fraction, okay, what would you get? You get 4 and you get 8n pi plus pi, or more simplistically, pi 8n plus 1 over 4, and that's another way that they could ask you to write it. And in the same way, if you have this formula here, what would you end up with? Well, you would end up with 2n plus 1 pi minus pi over 4, which you put into one fraction, which will give you 4 2n minus 1 minus pi, and with a little bit of shifting around, you get that as 8n plus 3 pi over 4. So realistically speaking, or really importantly, write down that when it's looking for the general solution of circular equations, it's looking for these things here, and the fact that sine has two formulas. You could almost argue actually so does cosine, but they just put that by this plus or minus, right? So they just do that by using this plus or minus. The very last section in the textbook, and wow, was this a long chapter, deals with identities. Right? And this is probably a chapter on its own. It's the idea of using rules to find various pieces of information, all right? And that is a long section that perhaps I'll leave for some other time, right? But it's not overly complicated. It's just using the ideas of finding one thing using formulas, right? I know that's a bit brief and probably not a great end of this particular video, but I think it's been long enough. So maybe, for revision, looking at exercise 6n would be pretty useful in that textbook. I'm going to call it a day for this particular one. We'll see you for differentiation and integration later on in the series.